we have a closed means isobaric, which means delta P equals 0, 2-liter container, so N equals, volume equals 0.002 meters cubed, holds 3 moles of gas, so N equals 3.00, and 200 joules of heat are added, so Q equals 200. We want to find the change in internal energy, delta U equals what? So first we're going to use the first law of thermodynamics, which is that the heat is equal to the work done on the environment plus the change in internal energy. And we want to find the change in temperature as well. So the change in temperature, or we'll use delta U equals N C sub V delta T, which is the same as N times, in this case it's a monatomic gas, that wasn't put in here, but it's monatomic, and the initial pressure was 100,000 pascals. We won't need the initial pressure for this part, but N C sub V is going to be 3/2 R delta T, which means we'll have delta U is delta U, since the work done on the environment is 0, so the delta U is equal to Q, so this is going to be 200 equals, our number of moles is 3 times 3/2 times 8.31 times delta T. And after a little bit of calculation, I get delta T is equal to 5.35 Kelvin. Now that pressure, in turn, is going to be delta P times V is equal to, since pressure times volume is nRT, we'll have delta P times V, since the volume is constant, times delta T. So our change in pressure times our volume, which is 0.002 meters cubed, equals the number of moles, which was 3 moles, times 8.31 times our delta T, which was 5.35 from above. And just using that answer from above, I get 66,666 pascals, which is about 2/3 of an atmospheric pressure. Now for the rest of the problem, we're going to have an open container and find the change in internal energy. Now with an open container, there's a different constraint here. It's going to be delta P equals 0. And we're going to add the information that the initial pressure was 100,000 pascals. Once again, we're going to apply the work environment plus delta U, this first law of thermodynamics. But this time it's going to be Q equals P delta V plus delta U. As a matter of fact, I think I'm going to run to the hints that I put online for this, because I don't really want to think about it right now. I have this 9-step process for the extra credit problem out here. Let's scroll down and get all 9 steps on the screen. We'll figure out the initial internal energy and initial temperature using PV equals nRT equals 2 over degrees of freedom times U, with our pressure of 100,000 pascals, our volume of 0.002 cubic meters. We had 3 moles of the gas constant of 8.31, and then we'll be solving for temperature and internal energy. Our initial temperature turns out to be 8.02 Kelvin, which is extremely cold. Turns out to be much colder than I expected, but the most popular monatomic gas, helium, boils at 4.2 Kelvin, so we're still within the range of possibilities. Just realized you couldn't see the entire calculation there, but that fixes that. And now the initial internal energy of the gas is let's call this T initial and U initial, is 300 joules. And we're going to add 200 more joules to that. See, what's this? We're going to find the change in temperature using Q equals NC sub P delta T. So I'll have 200 joules, which is equal to the number of moles we have is 3.0 moles, and C sub P is going to be 3 halves plus 1, or 5 halves. Let's just call it 2.5. 2.5 times our delta T. And I left out something fairly important. It's got to be 2.5 R, which is 8.31, which gives us a change in temperature of 3.2 Kelvin, and a final temperature, T final, of, we'll be taking 8.02 plus 3.2 for a final temperature of about 11.2 Kelvin. Now we can find U final by using PV equals 2 over degrees of, or nRT equals 2 over degrees of freedom U. Well, one of those. Probably makes more sense to just use the nRT part, which would be 3.0 moles times 8.31 times our new temperature of 11.23 equals 2 over degrees of freedom. Let's put that over here. The 3 halves on this side equals U, and that is U equals 420 joules. So delta U, there's something wrong here, isn't there? Delta U is, no, there's nothing wrong. Delta U is going to be U final minus U initial, and this is U final, so it's going to be 420 minus, here's our U initial, was 300 joules. 420 minus 300, which is 120 joules. So the next step is Q is work done on the environment plus delta U. So the heat added to it is 200. The delta U is 120 joules. The work done on the environment is going to be, a quick calculation gives me 80 joules. Now we can say the work done on the environment is pressure times the change in volume. So it's 80 equals 100,000 times our delta V, which comes out to 8 times 10 to the negative 4th meters cubed. Is our delta V, which is 0.0008 meters cubed, and our initial volume, or our final volume, is going to be equal to our initial volume plus our change in volume, which was 2 liters plus 0.8 liters, or 2.8 liters. So let's answer all 3 of these questions in one fell swoop. We have the change in internal energy was 120 joules. The final volume, was the very last thing I got, was 2.8 liters. And the final temperature was got earlier, 11.23 Kelvin.